All right, it looks like there's a few folks here. We're going to get started here in just a minute. Feel free at any point in time to say something in chat if you have a question about something. Hopefully you can see there's a chat box, wherever you're watching it. Hopefully you can find the chat box and can ask questions when you have them or make comments. And hopefully this goes well. All right, so before we dig into the lesson for this week, we have to talk about the exam. We have an exam next week in class, exam number 1. A few details about exam number 1. I got to get on the skinny marker. Exam 1 will cover all of chapter 6, including the stuff that we cover tonight. Well, I guess we're not going to cover 6.6. So chapter 6 except 6.6. We're not going to cover that section tonight. It's going to be an 80-minute exam. It's designed to take an entire class period for the classes that meet twice a week. And there are going to be 15 numbered problems. I say numbered problems because some of the problems have multiple parts. I think you saw there was a lot of your problems on the most recent homework. I think the 6.3 homework had a lot of problems with like 17 parts on them. Now, none of your test problems have 17 parts, and most of the problems are not multi-part. But when I say there's 17 problems, I want you guys to realize, okay, some of those problems have multiple parts. Now, one thing that is interesting in this class, I kind of like the idea of a 2-part exam. All the exams in this class are going to be 2 parts, including the final exam. There's going to be a calculator and a non-calculator. So one of the parts, and I can't remember which part is first. One of the parts is going to let you use your calculator. Calculator? Is that how you spell calculator? Okay. And then there's another part where you're not going to be able to use your calculator. Can we draw the unit circle on your test? You can draw whatever you want on your test. I don't know that there's going to be a whole lot of space for drawing the unit circle on your test. But yeah, I think that's actually a good, wherever there's space, I think it's a good idea to kind of start off with that kind of stuff. I usually tell calculator. I usually tell my students, like, write whatever you want on the test, especially this doesn't really apply to us, so I probably shouldn't. I'm not even going to spend time saying it. But yeah, when you get your test, I think it's always a good idea to just do a brain dump and find some spot on the test, whether it's on the front of the test or the back of the test or wherever there's space. Do a brain dump, get all of the stuff that you're trying to have memorized, get it all out on the page, and then when you need it, it's all there, as opposed to kind of trying to keep it all bottled up. And the unit circle is definitely one of those things that you can do that with. But like I said, I don't know if there's going to be a whole lot of space for doing that. Anyways, so the 2-part thing is interesting. Both parts are worth the same amount. There's actually 104 points available, so there's like 4 bonus points. You can actually do better than 100% on the test, so that's nice. I think that's something I know that's something that they do in 136 as well. So those of you who came from algebra, that's continuing on in trig. And so each part of the test is worth 52 points, and each part of the test you get 40 minutes for. So it's kind of an evenly split. Now, obviously, if there's 15 numbered problems and one part of the test has 7 and the other part of the test has 8, but they're roughly the same length in terms of the amount of content. Now, one way that you can prepare for the test, and the way that I suggest that you prepare for the test, here we go. This is our course page. If you go down to here we go. Link to text exam reviews. So these exam reviews are the key thing here. So there's Unit 1 review, and it'll have a list of problems. There is a non-calculator list of problems. So you should do these problems without your calculator. And then there is a there is a calculator permitted portion list of problems. Now, those of you who took 136 and did the exam reviews and practice quizzes for 136, I hope, realized that your exams looked exactly like the practice quizzes and exam reviews in 136. And it's the same thing this semester. These exam reviews, the problems that you see on your test look very, very much like the problems on the review. Okay? I mean, as much as problems can look like other problems, these review problems look like your actual test problems. So you should spend, I think, when it comes time to study for the test, you should just be doing these problems and figuring out how to do these problems and problems that are similar to like them. Now, one thing, I guess, these verify the identity problems. Those kinds of problems. It's kind of hard to find ones that look exactly like those, but you shouldn't expect anything significantly more challenging than these. Anyways, that's the exam review. And then if we go back to where we found that exam review, there is a Unit 1 review answer key. And so all the answers to most of the problems, the verify the trig identity, since there are different ways of getting those problems done, those solutions are not given. But the answers to all the other problems, I think, on this exam are, yeah. So you can see the graphs and things like that. We'll talk more about. This is what we're going to be doing tonight, is sketching some graphs. Let's see. Anything else? Oh, for this exam review, you have instructor's choice points assignment. To where is this? Yikes! There's all kinds. This student has not been doing anything and has all kinds of things to finish up. As I recall, this student had trouble seeing the last time I tried to do this. There we go. Test 1 review. I guess I didn't finish. Anyways, this is an assignment for instructor's choice points. So I want you guys to write up solutions to all the problems in that exam review that we just looked at. So just like you do for quizzes, write up solutions to all those problems. Now, you don't even need to print off that sheet, that review sheet. I don't even really want you to print it off. I'd rather you just write it up on your own notebook paper. Remember to write out all the problem statements and your complete solutions to all those problems. Again, those are for instructor's choice points, and I think it's a fairly significant chunk of your grade. I think it's like 10 points each or something. Anyways, you should do that, not only for the relatively free instructor's choice points, but also the fact that doing the exam review is going to be the way that you prepare well for this test. I made it abundantly clear that the exam review is the key to doing well, I think, on our tests. All right, so that's, I think, as far as what we're going to do next week, so we're going to have the first half of our class for a review. And if we were in person, you'd be seeing me make air quotes, because I'm not going to stand in front of the class and review concepts, okay? And I'm not going to pick a bunch of problems beforehand and do a bunch of problems and do those problems, because one of two things is going to happen. When I pick problems, I'm either going to pick problems that are on the test on purpose, because I know it's on the test, or I'm going to pick problems that aren't on the test. And either way, it's not the right decision. So what we're going to do is, when you do this exam review, if you have problems from the exam review that you're not quite sure of, you can ask me questions about that exam review. Or if you have other problems from homework that you're not quite sure of, you can ask me to do those questions. And so that's what we're going to do for the 80 or so minutes before the test next Wednesday, is you guys are going to just ask me questions for 80 minutes straight, and I'm going to answer them to the best of my ability. That worked really, really well for my algebra students last semester when we did it that way, and I'm expecting that it's going to continue to work well for us this semester. So those of you who are in chat, any other questions about the test before I move on to tonight's material? All right. I'm going to go ahead and take that as a no. If you guys do have questions, please feel free to contact me. I've been answering questions, it seems like, all day long. So I think the people who have been messaging me know I can get back to you pretty quick. You shouldn't necessarily expect that I'm going to get back to you right away, but I've been able to get back to people right away or relatively quickly for most of the semester so far. All right. So in order to get ready for the test, we got to finish up the last couple parts of Chapter 6, and the first part that we're going to do is 6.5, where we're going to dig more into the trigonometric graphs. Actually, we're going to be exploring the graphs of sine and cosine a little bit more closely. Sorry, I got to get something. I got like 9 different things going on right now. Got 3 screens, and one of them just went out. Oh, there we go. All right, so I want to start off by looking at the graphs of sine and cosine and maybe plot a few points. We didn't do this last week, but if we want to, for instance, plot the graph of y equals, gotta go skinnier here. Sketch the graph of y equals sine x, for instance. We could plot some of those points from the unit circle that we know. Like, for instance, we know, we know pi over 4. And we know, I guess, pi over 3 is right about there. And pi over 6 is on the other side. And let's see, sine of pi over 3. Sine of 0 is 0, so we can plot that point. Sine of pi over 3 is 1/2. That's a little bit lower than 1/2. Sine of pi over 4 is root 2 over 2. Let's see if I do on my calculator that I got here. If I do... Oh, God, I don't know this calculator. Where's my square root button? There it is. If I do the square root of 2 divided by 2, I get about... Oh, come on. That's not helpful. That's not helpful. I think I want to do that. Classic? Oh, God. I don't know how you guys use this calculator. All right, square root of 2 over 2. Is this going to happen? Is this going to happen? Yay. It's about 0.7. All right, so almost 3/4 of the way up. So there's root 2 over 2 for pi over 4. And then we'll go up to root 3 over 2. Is probably, I think it's 0.8 something. Root 3 over 2 is up there for pi over 6. And then sine of pi over 2 is 1/2. Or sorry, sine of pi over 2 is 1. And then we could come back down the other side and plot some more points. I don't want to take too much time to plot points. But anyways, that's kind of, if you're plotting points, that's kind of how you get the rough shape of the sine curve. And then it comes back down. So I plot the important points in terms of I figure out where my intercepts are. And also we have these things called maximums and minimums. It's kind of basically where the curve hits the top of a hump or the bottom of a hump. Okay? And all right, so if we were to just plot all the points that we know on the unit circle and connect them, then we get that shape. We get that shape for the graph of y equals sine x between 0 and 2 pi. And then we could use periodicity to kind of repeat the graph. So there's this part of the graph that's going to get repeated on this interval here. And then this part of the graph gets repeated another 2 pi later, and so on and so forth. All right, going back the other way, this part of the graph here is going to get repeated back here. If I subtract 2 pi, and this part of the graph here is going to get repeated right here. And the last 2 pi interval, that was disgusting, but that's our graph of y equals sine of x. Hit the arrows above the enter sign. I should probably play around with that calculator a little bit more so that I can show people how to use it. Okay, so there's our graph of y equals sine of x. For y equals cosine of x, I'm still going to draw, I guess the book I think refers to it as a cycle, as opposed to a period? Doesn't it start with 0 and go to pi over 6 first? I'm not exactly sure. Oh, pi over 6. Wow, you're right. Whoa, what's wrong with me? Pi over 6 is, there we go. Man. Not starting off well tonight. That's pi over 6, and that's pi over 3. My brain was thinking one thing, and I wrote a completely different thing. Yeah, you're exactly right. You're exactly right. All right, for the graph of y equals cosine x, for both of these, we usually start with x equals 0, and cosine of 0 is equal to 1. So we're going to start up here for cosine of x, and then it goes down over its first quarter of a period, and it keeps going down for the next quarter of a period. So when I plot these zeros and maxes and mins, it kind of bounces back and forth between 1 and 0 and minus 1. Sine does exactly the same thing, except for the difference here is, I guess I think of sine as starting at 0, and I think of cosine as starting at 1 when we think of, again, what your book calls the cycle, the primary cycle of these graphs. Anyways, cosine is going to go down like that, and then curve that way, and then up that way, and then that way. So that's what one cycle of the graph of cosine looks like. And then if we do use the periodicity or repeat values, it's just going to repeat itself for the next 2 pi period. And if we want to go backwards, the next part of the graph is kind of a copy, if I'm going backwards, of that part of the graph. I guess thinking about the last pi over 4, or sorry, the last pi over 2 of a period. And then like that, which is a copy of this part of the graph. And then back like this. All right, so there's our graph for y equals cosine of x. They have, now if we look at the graphs of sine x and cosine x, they have the same shape. They're doing exactly the same thing. It's almost like, well, wherever sine is going, cosine gets there pi over 2 ahead. Okay, so cosine starts at 1. It takes sine pi over 2 to get to 1, and then by the time sine gets to pi over 2, cosine's already back down to 0. So I think of cosine as being like pi over 2 ahead of sine of x, is one way to think about it. And we'll have some trig identities that help us to understand that later on in the course, not tonight. Okay, so these are the two graphs. These are going to be kind of our foundation for all the problems that we're going to do for the first half of class tonight. These two pictures, and they're going to be the only ones that we work with. We're not going to do anything with secant and tangent or cosecant or cotangent. Those graphs would be covered in section 6.6, but we're not going to cover section 6.6 in our class. Now, so we're going to be using these graphs, and we're going to be applying graph transformations. So if you go back to section 3.5 in your textbook, where you learned, 3.5 is where you guys initially learned about graphs of functions. So that's where I grabbed all of these little tables. So if you remember, if you've got a function, for instance here, if you got a function g of x, and you want to know, if you got a function f of x and you want to know what the graph of y equals f of x minus c, so subtracting a positive number on the inside, that's a horizontal shift to the right. The stuff that goes on the inside is the part that's hard. So you've got horizontal shifts by adding or subtracting numbers on the inside of a function, and I guess the shifts happen the opposite way that you would expect them to. A minus, subtracting a positive number means that you shift the graph to the right, and adding a positive number means that you shift the graph to the left. On the other hand, when you add or subtract on the outside of a function, that shifts the graph up or down. We're not going to do too much of that until right at the very end of this. Now that's adding and subtracting on the inside and the outside. If I want to multiply on the inside, if I've got a number that's a positive number that's bigger than 1, then that corresponds to compression, horizontal compression. We're going to use that here in a little bit. And then multiplying by a number between 0 and 1 stretches horizontally. Now, I didn't realize it didn't mention here, but when we'll talk about that when we get to the example. We don't necessarily need to review everything here. Again, I guess this stuff that goes on the inside happens the opposite way that you would expect it to. Then things that happen on the outside. For instance, if I multiply by a number bigger than 1 on the outside, it does stretch it out vertically. And if I multiply by a number in between 0 and 1, it compresses it vertically. So these are the graph transformations. There's one more that's remember when you have minus signs, like multiply by a negative number. There's some reflections that go on. We'll cross that bridge when we get to an example here in just a little bit. This is going to be the foundation of our work initially, but we're building towards some formulas. By the end of the section, we're going to have some formulas that are going to allow us to get around needing to do this graph transformation every single time. So that's the good news. The good news is that we're only going to really need to, I need to use these ideas to explain some things until we get there, but you're not necessarily going to have to use this stuff in order to get the job done yourself. Okay? Now, the other side of this is later on in the semester, we're gonna stop doing trig and start doing a different thing called conic sections. And when it comes to doing conic sections, like understanding these graph transformations can potentially make that stuff very easy and significantly reduce the amount of memorization that you have to do. So I would encourage you to try to understand this stuff in terms of graph transformations, and at the same time, be able to use the formulas to get the job done quickly and easily without thinking too hard about it. All right, so let's go ahead and get into some problems here. First problem here, we have 4 functions that we want to graph, all on the same axis, so that we can look at an idea. The first is the graph of sine of x. So I'm going to go ahead and pop that graph in real quick. Remember, it starts at 0, goes up to 1, back down to 0, down to -1, back up to 0, and there's 1 period of it. Now, if you've got some colored pencils at home, that might be useful here, or some good labeling is also helpful. And then we'll use periodicity to kind of repeat the pattern. And going back the other way, wow, that last little bit was terrible. For some reason, I have more trouble going when I go to the left than when I go to the right when I'm sketching this stuff on my tablet here. All right, so there's the graph of y equals sine of x. When we go to graph g of x here, 2 sine of x, so we're multiplying by a number bigger than 1 on the outside. That's a vertical stretch. I'm going to take these key points, my zeros and my maxes, and plot those. Those are the key points that you really want to plot. All right, we plotted a few points at the very beginning. The points that you really want to plot are the zeros. All right, so when I stretch out 0, when I multiply 0 by 2, it doesn't change any of the zeros. 2 times 0 is still 0. Okay, so for instance, sine of negative pi is 0, and 2 times sine of negative pi is still going to be 0. All right. Now, the ones, when for instance, sine of pi over 2 is 1, and so 2 times, so if I do g of pi over 2, that would be 2 times sine of pi over 2, which is 2 times 1, which is 2. All right, so we can plot that point. In a similar fashion, when I go out to 3 pi over 2 and plot g, it's going to be negative 2. It takes negative 1 and stretches it out to negative 2. At 5 pi over 2, it again stretches it up to 2. I think you guys are starting to see the pattern here. At 7 pi over 2, it stretches that negative 1 down to negative 2. And we're just stretching things out everywhere vertically. Again, multiplying on the outside by a positive number stretches it out if the number is bigger than 1, and compresses it if the number is smaller than 1. All right, so we will just go ahead and connect all of these red dots with nice curves. All right, here we go. All right, so that's the graph of y equals 2 sine of x. If we go to look at h, we can do a similar analysis and say, well, now I'm multiplying on the outside by 1/2. Instead of stretching it out by a factor of 2, it's going to shrink everything by a factor of 2. Or, I guess, everything's going to be half as high. So all the zeros still are at 0. That's the nice thing about stretching out 0 is it doesn't go anywhere. But then now all my peaks and valleys, well, all my peaks are going to be at 1/2 now. And all my valleys are going to be at minus 1/2. That's not even close to 1/2 there. There we go. All right, a few more points to plot, and then we can connect the dots here. There is the graph of y equals 1/2 sine x. All right, that's not too bad, I guess. I think the vertical stretching and vertical shifting were the easier of the graph transformations to sort out, and they're not too bad here. The last one, k of x, is negative 2 sine of x. In addition to stretching it out by a factor of 2, this minus sign here, this minus sign means we're going to have to flip things across the x-axis. So for instance, k of pi over 2 would be negative 2 times sine of pi over 2, which is negative 2 times 1. Sine of pi over 2 was 1 up here, which is negative 2. So it takes, first off, all the zeros are going to stay 0. Again, that's one of the nice things about the x-intercepts don't change when you are stretching or compressing vertically. And I kind of think of this as like a two-stage thing where we're going to go ahead and stretch it out by 2, and so we're going to go up to the peak here and then flip it across the x-axis. So remember, multiplying by negative 1 on the outside corresponds to a reflection across the x-axis. So I'm thinking about my graph of g here. Actually, I'm reflecting the graph of g across the x-axis. Okay. Now I could just reflect it, but I just like to plot all these points. They give me a nice target to shoot for. So I can just kind of focus on one little segment at a time. God, that was awful. Now, when you're graphing these on your own, I would encourage you to, try to make them look nice. Try to indicate some curvature that's going on, but it doesn't necessarily have to be perfect. But what we definitely don't want is just spikes everywhere. There's definitely not a spike at any of these humps. All right, there's a nice round edge. Okay, so those are the graphs of all of those functions. Again, we got those graphs by thinking about stretching and flipping vertically because we were multiplying by constants on the outside. All right, now in the context of sine and cosine functions, let's just sneak back to the graphs of those functions. They oscillate. That's a fancy word for the behavior here. They oscillate between plus and minus 1. They never get outside plus or minus 1. That's a new idea in terms of graphs. The graphs that you guys looked at in your algebra class were all graphs of polynomials, exponential functions, and logarithms, and those graphs were unbounded. All right, all of those graphs eventually either went down to negative infinity or up to positive infinity. If you went far enough on either, like out to x equals a big number or x equals a big positive number, the graphs ended up shooting off to infinity. Whereas these two graphs just kind of stay in the pocket. They're in that +1 to -1, or sorry, -1 to +1 pocket. Okay, and so for these graphs, we have this new idea of what's called amplitude. Okay, for a sine or cosine function. Now, your book gives a definition that doesn't exactly work. Your book's definition works just fine here, but it stops working later on. And so we're going to go ahead and ignore their definition and say that it's the half height of the graph. Okay. Now, for instance, the height of the sine function here, it goes from -1 to +1. So the height of the graph, I would call the height of the graph 2. And so the half height is 1. All right. So that's what I mean by half height. All right. Now in your notes, I think I should have your notes available. In your notes, there's a couple questions there that we can think about. What are the amplitudes of the functions that we have here in this example? All right. We just talked about sine. Sine goes from -1 to +1. It has a height of 2, and so it has an amplitude of 1. The amplitude here is 1. We usually use the capital letter A for amplitude in this class, or at least, I guess, in the context of problems where we're talking about amplitude, that's the parameter. That's the parameter name that's given to it, capital A. For G, the height. Let's see, the height of G goes from -2. A lowest point of -2 up to a highest point of 2. The difference, the total height of the graph is 4, and so the half height here would be 2. All right, so the amplitude here is 2. For h of x, it looks like its lowest valley is at -1/2 here and here and here. Got 3 places where it's -1/2. Its highest point is +1/2, and so its total height is 1, which means its half height is 1/2. And then for k of x, now just like g of x, its lowest point is at -2, and its highest point is at +2. The total height of the graph is 4, and so its half height is 2. So the amplitude here for k is also 2. And hopefully you're starting to kind of see maybe a relationship between this amplitude and this constant multiple on the outside that happened. And so when we go to answer the question, all right, if I have f of x equals a sine x, or g of x equals a cosine x, a. So we're multiplying on the outside by this number a. Well, it's, I guess, a first stab at it would say, all right, the amplitude must be the number a. But notice here in my k of x, the amplitude wasn't -2, it was +2. So the amplitude is actually the absolute value of that constant multiple on the outside. All right, so hopefully that all makes sense. As always, stop me if you have questions. Then moving on to the next problem, number 2. We have a similar problem. Now we're going to work with cosine. Sketch the graphs of the following functions on the same coordinate axis. If we start with the graph of cosine, again, that's our kind of jumping off point. I think of the cycle, as starting at 1, going down to 0, down to -1, back up to 0, and up to 1. And so there's the graph of one cycle of the cosine function. And then it just repeats itself. Now, one of the goals here, by the way, guys, one of the goals in this whole section, well, one of the goals is so that we can kind of review some things about graph transformations, because that's going to be really beneficial later, like I said. But another thing is so that we can, it's another opportunity to just start nailing down some of these special values of sine and cosine, in particular where they hit 0 and where they hit the plus and minus 1. And it's also an opportunity to just get, to just drill into your head what the shapes of these graphs are. So, use that opportunity, use the opportunity to get good at it. All right, so now for cosine of 2x, now we're multiplying on the inside. In all these examples, we're multiplying by a positive, well, I guess in the first two examples, we got multiplying by a positive number on the inside. And remember, that has the effect of stretching or compressing horizontally, and it's kind of the opposite of the way that you would think. Okay, now here our zeros our points are gonna move. Okay, the points along the y-axis now are there's only one point on the y-axis. That's the one that stays put. If we go back to the previous example, the points on the x-axis were the ones that stayed put. Here it's the points on the y-axis are staying put, and everything else is kind of getting, I guess in the case of cosine of 2x, we're compressing horizontally. Everything's getting closer, okay? So instead of taking pi over 2 to get back down to 1, now it takes pi over 4 to get back down to 1. And instead of making us go all the way to pi to get down to -1, now we get there in half the time. We get there in pi over 2. And so when I go to plot my zeros and ones and -1s, instead of them all being pi over 2 apart, they're pi over 4 apart now. Okay, so let's just go ahead. Now we got lots of cycles that we can draw here. Instead of just, I guess our original graph just had 3 cycles. This one has twice as many cycles in the same amount of space, because you can kind of think about it oscillating twice as fast. Oh, that's what that 2x means. It's oscillating twice as fast. Okay, now we might have a way of understanding why. That's a better way of understanding that too. All right, so there's all of our cycles on the positive side of the x-axis. If I go ahead and plot my points here again, trying to be careful to remember to get my zeros and ones to be exactly pi over 4 apart. I almost messed up there. Let me go back this way. All right. Starting to get sloppy because I want to go fast. So we get, again, the cosine of 2 times x. It has the effect of, again, smooshing the graph together. Think of it like a spring. It's kind of easy to think of these sine and cosines kind of looking like springs. Like if you were to draw a spring, your picture would kind of look like that. Well, maybe, I don't know. It depends on how. Maybe not. I don't know. Anyways, if you were to draw a stretched out spring, it would eventually look like a sine or cosine graph. And you can think of, the cosine, when you compress that spring back together, you get the coils being closer together like we have in the red picture here. All right, when we go to graph h of x, we're multiplying by 1/2 on the inside. And that has the effect of stretching out the graph by a factor of 2. So again, our point on the y-axis is going to stay put. But now this point right here at pi over 2, 0, it gets stretched out to being at pi 0. And this point down here at pi 1, it gets stretched out to 2 pi, negative 1, sorry. So now our zeros and ones and negative ones are now pi apart instead of 2 pi apart. So now we only get one complete cycle on the right side in this 4 pi interval from 0 to 4 pi. We only get one complete cycle. And if I go back the other direction again, our zeros and ones are now pi apart instead of pi over 2 apart. This is what the stretched out. Again, we're stretching out horizontally. That last little bit was nasty. I'm going to go ahead and redo that. Didn't hit my target at all. All right, that's a little bit better. We'll go ahead and keep that one. All right, so there's my graph of h of x. Again, multiplying by 1/2 on the inside has the effect of stretching it out horizontally by a factor of 2. Or you can think of stretching it out horizontally by a factor of 1 over 2, 1 divided by whatever that number is. Now, in your algebra class, you would have understood multiplying by negative numbers on the inside. You would have understood those as corresponding to reflections across the y-axis. Why are my x and y-axes not labeled here? Whoever made this graph is terrible. We should always label our axes. At least that's what that's not the y-axis. Anyways, we would normally think of multiplying by a minus sign on the inside as corresponding to a flip across the y-axis. But since we have some properties or formulas for negatives, the even and odd properties, we'll have a better way of dealing with those. So in this case, k of x is cosine of 2x. Well, let's just write it all out. All right, k of x itself is cosine of minus 2x. And since cosine is one of the even functions, it kind of destroys that minus sign. So it's just the same as cosine of 2x. So we don't need to really worry about we got to worry about it a little bit, but we don't have to have a special tool for dealing with horizontal reflections or reflections across the y-axis because we have these even and odd properties for sine and cosine that I think are maybe a little bit easier to deal with. So actually, the graph of cosine of negative 2x is the same as it's the green graph is be the same as the red graph. Okay. All right, so I'm not going to finish drawing. The green graph would have been the same as the red graph. So I guess if I was doing some good labels here, we'd have, all right, the black graph is y is equal to cosine x, and the red graph would be y is equal to cosine of 2x, which is also the same as cosine of minus 2x. And then the blue graph would have been y is equal to cosine of 1/2 x. Now these horizontal stretches correspond to an idea with the trig functions related to the period. We talked about periodicity. That's the repeated values is related to the periodicity of these functions. The period of the graph of a sine or cosine function is the length of the smallest interval on which the graph does not repeat itself. Okay, so for the cosine function, when we draw that first cycle, starts at 1, and we don't get back to 1 until it hits 2 pi. And so that's when we start repeating ourselves. So the period here, we use the capital letter T for the period often. The period for our cosine function is 2 pi. We talked about that last week. And these horizontal stretches affect the period. They change the period. The vertical stretches change the amplitude. The horizontal stretches, multiplying on the inside of the function, those affect the period. All right, now the graph of cosine of 2x. Again, if we just look at the first cycle, it starts when x is equal to 0, and then we go down and back up and get back up to 1 at x equals pi. All right, and over that whole interval, obviously we have some repeated values, like that value and that value are the same. We have some repeated values, but we don't have those values. The graph doesn't repeat itself. Like here, if you think about moving from right to left, we hit this one while the graph is going down, and we hit the other one while the graph is going up. Right? So we kind of hit those points at two different kinds of places along the curve. Anyways, the period for this function, we get one complete cycle between 0 and pi. The period here is going to be pi. Now remember, in the last example, the amplitudes, the values of the amplitude ended up somehow being related to that constant multiple that we started with, and we're going to see the same kind of deal here. Okay? So see if you can recognize a pattern as we're discovering these periods. For the cosine of 1/2 x, let's see, we start at 1, and then it takes us actually the full 4 pi to get back up to 1. So the period for h of x would be 4 pi. And then for cosine of negative 2x, remember that was the same as the graph of cosine of 2x. The period there would also be pi. Okay, again, those two graphs were the same graph. They're going to have the same period. They're going to have the same period, the same amplitude, the same just about everything. Okay, so there's some horizontal stretching and how the horizontal stretches and compressing affects the period. If we want to know, I guess the big question here, what is the amplitude and period of f of x equals, let's just focus on the cosine one here. It's going to be the same answer for sine. If I have f of x equals a cosine bx, well, we determined before that the amplitude is going to be the absolute value of a. We didn't see any problems here where the amplitude changed at all. And then if we look at, let's see if we can identify the pattern here. All right, so when the constant on the inside was 1, that was our black graph, then we got the period was 2 pi. Okay? So, I guess we got two options here. In the previous problem, well, I guess we didn't see anything in the previous one. Again, we're just trying something new here. All right, so when b was 2, my period was pi. When b was 1/2, my period was 4 pi. So we have a base of 2 pi, whereas with the amplitude, kind of our generic amplitude was 1, and then we ended up multiplying that amplitude by whatever the outside constant was, right? That's what we had in the previous example. All right, our amplitude basically corresponded to that multiple. Here, we have kind of a vanilla version. The vanilla cosine function has a period of 2 pi. And then if I want to try to incorporate the coefficient, it looks like, well, here it's like I'm taking 2 pi divided by 2. This one's 2 pi divided by 2. This one's 2 pi times 2, which is the same as 2 pi divided by 1/2. So your initial good guess would be that the period would be 2 pi divided by whatever that b value is. But once again, we have to take the negative case into consideration and do the absolute value of b. So that's how you can find the period here. And the fact that we have to divide by b when it's the inside multiple, I think that makes sense because it's the opposite of what the stuff that goes on inside the function is kind of the opposite of the way that you would expect it to be. For what it's worth, I think of instead of thinking about the the stuff inside the function is affecting the graph, I think of the stuff on the inside of the function as affecting the x-axis. So stretching out the x-axis by a factor of 2 makes it look like the graph is being compressed by a factor of 2. But I don't think that's very helpful for most students. I've tried to push that on students in the past, and it wasn't very helpful. All right, so that's period stuff. That is multiplying on the inside. The last thing that we want to deal with is adding on the inside. We're going to go ahead and start with our sine function once again. So let's get that drawn reasonably quickly. Starts at 0, goes up to 1, back to 0, down to -1, back to 0, up to 1, yada, yada, yada. And then go in the other direction, down to -1, back up to 0, up to 1, back down to 0. So hopefully we're already getting sick of sketching these functions. By the way, y'all's homework for next week is brutal. In addition to having, I think, a relatively brutal WebAssign, like I looked at it, they are crushing you guys with homework this semester, and I don't necessarily have a problem with it, but it's something that you guys want to handle. Find a way to get it done. The practicing is a huge deal with these problems. So that's the repetitive nature. That's the repetitive nature. I know it kind of sucks, but just keep going. Those of you who are doing well, keep at it. Keep at it. All right, so there's the graph of y equals sine of x. Now, if we want the graph of g here, x minus pi over 2, remember, adding and subtracting on the inside has kind of the opposite effect. It seems like, all right, if I'm subtracting pi over 2, that I should move everything to the left, but it's actually the opposite way. We move it to the right. And so I'm going to take this point that's at 0, x equals 0 and y is 0, and move it out to x equals pi over 2. And this point here that's at x equals pi over 2, I'm going to shift it to the right. I'm just shifting all my points to the right. This point down here gets shifted to the right, pi over 2. This point here gets shifted to the right, pi over 2. And so on and so forth. Everything on the other side also gets shifted over pi over 2. There we go. Up here. Back down here. And then there was a point over here off the graph that we didn't plot that got shifted there. All right. So the adding and subtracting on the inside corresponds to shifting horizontally. And again, you kind of shift the opposite direction. That seems intuitive. All right, so there's our graph of y is equal to sine of x minus pi over 2. In C, we got pi over 2 minus x, and all right, I'm going to go ahead and use a little bit of algebra as well as some formulas for negatives. This is the same as sine of negative x minus pi over 2. If I factor out a minus sign and kind of rearrange the order on the inside. And then remember, for sine's an odd function, and so the negative comes out. Cosine eats it up. Sine lets it pass through. Okay, so instead of thinking about this as multiplication, I guess this really is also the same as sine of negative x plus pi over 2. And so there is a way to think about this in terms of a shift and a horizontal flip, but I think it's better to think about it as a shift and a vertical flip. So we're going to take this sine of x minus pi over 2 that we just got done drawing, and then just flip it. This is a minus sign on the outside. We're just going to flip everything across the x-axis. So this point gets flipped over here. All the zeros stay the same. That point gets flipped down to -1. 0 stays at 0. -1 gets flipped up to +1. 0 stays at 0. +1 gets flipped down to -1, and so on and so forth. All right. So here is the graph of sine of pi over 2 minus x. Now, if I were doing this on like Desmos or some other graphing software, I would erase, at this point, I would erase the red and black curves and ask you guys, what is this blue curve? What graph does this blue curve correspond to? And of course you would say y is equal to sine of pi over 2x, but then hopefully you would also recognize that it's the graph of cosine of x. Okay, this blue graph that we just drew at x equals 0, we start at 1, down to pi over 2, down to -1, so on and so forth. That is the graph of y equals cosine of x. So hey, here's a new trig identity. We're not learning this trig identity today, but we can at least understand it today so that when we get to it in a month, that it won't be that big of a deal. But there's a trig identity. It's one of the cofunction identities. We're going to learn the cofunction identities later on. Notice that pi over 2 minus x, you can think about that as 90 degrees minus x is the complement of complement of x. All right, so there's a little bit of an aside, a fun thing that we were able to look at here. All right, so those are a couple of horizontal shifts related to sine of x. If I look at sine of 2x, draw the green graph. Remember, sine of 2x is going to stretch. It's going to. I just lost it. It's going to compress everything by a factor of 2, right? Sine of 2x is going to compress everything by a factor of 2. Yeah. All right, so when we compress all of the things on the sine graph by a factor of 2, now our period gets cut in half. It oscillates twice as fast. Every pi over 4 instead of pi over 2 is when we get a new point. This is getting all kinds of messy, isn't it? All right, so let's maybe just draw the first couple of cycles of this so that we can move on to the last picture here. He says, and then he draws all of them, because I got a little bit of that OCD. It's got a little bit. All right. And then I guess we should probably go backwards too. Whenever I cut corners, whenever I get like a little bit impatient and start cutting corners, that's when like 5 minutes down the road, I was like, I wish I would have just taken 30 seconds to draw the other part of that graph, and then we'd have everything there that we wanted, and I don't have to regret having skipped over something. All right, so there's our graph. There's our graph of y equals capital F of x. By the way, if you haven't started recognizing that like the capital letters and the lowercase letters are different letters, and you should just use the ones that we give you, please start doing that. Capital F and lowercase f are two different letters, and so you shouldn't use a capital F when I'm using a lowercase f, and vice versa. It's not so much what I'm using, it's whatever's being used by the problem. All right, now g of x, it might seem tempting to just move everything to pi, But that's not how those inside shifts work. All right? How this is really working, and this is one of those things that's one of the parts that makes the graph transformations confusing. What's really going on here is that I'm doing the horizontal compression by a factor of 2, and then I'm shifting, well, since it's a plus here, I'm shifting to the left pi. So I'm going to take this green graph, and shift all the points to the left pi. All right, so this one gets shifted to the left pi. This one gets shifted to the left pi. This one gets shifted to the left pi. And it's not, we're starting to see, I didn't do this on purpose, by the way. It's the same graph. It's the same graph. Now that's because for D, you could do either. You could say, hey, that's sine of 2x as well. It doesn't really matter. The fact, we gave this function a name, so it doesn't really matter which one we call it. There is a distinction. I guess there's a distinction which one you use. But it's not an important distinction, and it's not something that we need to worry about here. All right, now we just figured out that g of x was the same as f of x. But I guess like I said, this wasn't intentional. We want to recognize that I guess the key thing here is that we ended up shifting by pi. All right, we ended up shifting by pi to the left. That's what we wanted to see. Okay. Now these horizontal shifts, in the context of sines and cosines, we call those phase shifts. This is the parameter or variable, if you want to call it a variable. The variable that's used to talk about phase shifts. I don't think our book uses the A's and the T's and the P's. I think those are mine, but I think it's a fairly standard thing to use capital A for the amplitude, capital T for the period, and phi. This is the Greek letter, or at least one way to write the Greek letter phi or phi. I say phi. Sometimes you'll see phi drawn that way too, or that way. I'm not exactly sure why there's multiple different ways to draw phi. But anyways, that's what that is, the Greek letter phi. But the phase shift would be after you've done all of the stretching. I guess the definition here is a little bit confusing. All right, so we have y equals a sine of bx plus c, y equals a cosine of bx plus c. It's the amount of shift relative to the graph of a times sine bx. So I guess your starting point is after you do all of the vertical and horizontal stretching, then you shift it. That's the phase shift. So when we focused on this g of x, for instance, we realized, okay, I was stretching first, or I guess in this case, we were compressing by a factor of 2. We do the compression first, and then I shift by pi to the left. So I guess technically the phase shift there would be negative pi. So I guess that's one of our answers. One of our answers to the next problem, the next part here. What are the phase shifts in 2? Well, in part E, our phase shift was negative pi. Again, this value here. For f of x, well, it is its own version here. There's no shifting from all of the stretching stuff. There was no shifting, so our phase shift was 0. For h of x, when we're talking about the shift from the graph of how do I get from black to blue? I have to shift to the left pi over 2, right? Or I guess you could also shift to the right. What is that, 3 pi over 2? So there's kind of two different ways that we could have gone here. We're going to go ahead and say we shifted back pi over 2. So our phase shift here was minus pi over 2. To get from the black to the red, here we shifted forward pi over 2. And then for the phase shift, we're going to go ahead and deal with that. I guess it's kind of hard to see the pattern here. It's kind of hard to see what the pattern here. There's a relationship. Notice that our b value in this g of x example, the b value comes into play. The b value comes into play. So let's go ahead, move on to the theorem on amplitudes, periods, and phase shifts. And here's where we get a bunch of formulas. And we don't have to think about graph transformations anymore. I mean, you still could, but it's probably best to go with just the formulas. The amplitude, that was the easy one. The amplitude is the absolute value of A. The period was also not too bad. The period of these, the A sine bx plus c and A cosine bx plus c would be 2 pi divided by the absolute value of B. And then the phase shift, it turns out the phase shift is given by minus c over b. Now notice here our versions, I guess our jumping off versions have a plus c. The fact that we have to negate that is because of the plus a positive number means shift to the left and minus a positive number means shift to the right and all that confusion. So that's where this minus sign comes into play. The divided by b part, that's where the stretching, the horizontal stretching or compressing, how that affects also not only the period but also the phase shift. Okay, so we've done a lot. We've done all the heavy lifting we need to do to try to maybe understand these formulas just a little bit. Ultimately, you're going to want to just know those formulas. But if you have trouble with those, if you know, some people run into an issue on tests where they just completely draw a blank when it comes to things that they're supposed to have memorized. I've found that if you have a way to think your way through it, then it's easier to remember the formulas. All right, knowing that the amplitude is affected by, it's a vertical stretching, so it's got to have something to do with this A coefficient. All right, the period is being affected by the horizontal stretching, so it has to have something to do with this B. Okay, but now that we have those formulas, we don't have to think about these things in terms of graph transformations anymore. And as much as it pains me, I would encourage you guys to just memorize these formulas and know how to use them. Okay. Now, another formula that you can, or another fact that you can use here, you don't necessarily need to, but I think it would be useful, is an interval containing exactly one cycle can be found by solving this inequality. All right. So we're going to go ahead and do that. This is more of a graphing tool than it is anything else. You're not going to have any questions that ask you to produce this interval. You are going to have several questions that ask you to produce the amplitude, period, and phase shift. In fact, all of the remaining examples here, we're going to have to produce the amplitude, period, and phase shift. When it comes time to graph, dealing with it this way is one of the easier ways of dealing with it. All right, we'll have other ways that maybe I'll show you, but for the first couple, we're going to go ahead and maybe solve this inequality when we go to get the graphing. I might have to refer back to that. By the way, I don't do this. I personally don't do this. I will show you what I personally do, but when I have to go back and refer to this, that's why, because I don't usually do it. I don't have that one memorized, and I don't ever really need it. So, anyways, if we want to find the amplitude, period, and phase shift for this function, well, the first thing is, hello, Neil. For the phase shift, can we use the interval instead? I guess I don't understand the question, or maybe I do. I guess when it asks for the phase shift, it wants a specific number. Now I suppose, yeah, no, I think for the phase shift it wants a specific number. So you should just do the minus c over b, and you completely, it's minus, this is little c and little b. But yeah, I think when it asks for the phase shift, it just wants that specific number. Definitely on WebAssign. It just wants that number. Now, I guess it boils down to, all right, if you write down the interval on a test or a quiz, then I'm going to give you some partial credit because you're giving me information that's relevant. But I can't give you full credit because you haven't told me what the phase shift is. Like there's a vocab test part of doing math stuff where it's like, do you understand? Like, can you tell me what I mean when I say this word? So make sure that phase shift is that horizontal shift that happens. All right. Anyways, find the amplitude, period, and phase shift. Well, first it might be helpful to identify all of your parameters here, A, B, and C. So little a is 3 in this case. B is 1, right? We're thinking about, I guess, the basic version is y is equal to a cosine of bx plus c. So writing it in that form was a good first step. Anyways, a is 3 here, b is 1, and c is pi over 6. And so when we go to find the amplitude is the absolute value of 3, which is just 3. The period, the period is 2 pi over the absolute value of b, so that's just 2 pi. And then the phase shift is minus c over b, that's minus pi over 6 divided by 1, which is just negative pi over 6. All right, so there's our amplitude, period, and phase shift. When we go to find the right interval, we're solving for 0 is less than or equal to x plus pi over 6 is less than 2 pi. Well, I guess that's easier than I thought it was. You just take the junk that's inside the parentheses, right? That's not hard. That's not hard at all. Okay. Okay. And when I solve that, well, we got this compound inequality. We can subtract pi over 6 from all sides. Let's see, when you do 2 pi minus pi over 6, that's 11 pi over 6. 12 pi over 6 minus 1 pi over 6 gives 11 pi over 6. Yeah, I think this phase shift is one of these things where you might, depending on who the teacher is or what textbook you have, they might have different definitions for the phase shift. Like there might be some textbooks or some teachers that tell you that the phase shift is the interval where you graph one cycle. And so I think amplitude and period, roughly, that's roughly standardized language, and everybody means roughly the same thing when they say amplitude or period. But with phase shift, different teachers might mean different things. And in this class, phase shift is the number. Phase shift is the not only the amount of shifting, but also the direction of the shift. And so we want this number. But anyways, here what we've just determined is that if I sketch the graph I'll get exactly one cycle on the interval minus pi over 6 to 11 pi over 6. All right, so I will attempt, let's see, I got to go a third of the way back to get to minus pi over 6. And then 11 pi over 6 is a third of the way along this interval. Oops. I almost did it again. 11 pi over 6. Now what I usually do when I draw these is I basically cut this interval that we just found, I cut that into fourths. So the halfway mark is right there. So what's that's going to be 5 pi over 6. And the halfway mark in between those 2 points is there. I think that's 2 pi over 6 or pi over 3. And here will be 8 pi over 6 or 4 pi over 3. So I basically found my interval and my kind of quarter periods. My quarter periods. Or here, if I wanted to find my quarter periods, I could just take in my actual period and divide it by 4. Okay? Anyways, all right, so now I've got my important parts marked out on the x-axis. And then, let's see, now we're going to go ahead and take into account that my cosine graph starts at 1, but I have a amplitude of 3. So this cosine graph is going to start off at 3, and then go down to 0, and then down to negative 3, again, at these quarter period marks, back up to 0, and then up to 3, and then there's one good cycle of the graph of this function. And if I wanted to draw another graph, now it's kind of clear that from my previous periods that, all right, I'm just going to get these tick marks a third of the way to the left of each of the major hash marks. You can use periodicity stuff here, as well as some of the other patterns that you recognize in the process of getting that one cycle drawn to draw the rest of the graph. So now we're just using periodicity to get the rest of the job done. Now the fact that the period didn't change for this graph made this one a nice one to start off with. I was going to say it made it a little bit easier, but that just means it's a good one to start off with when we're doing multiple things at once. All right. So that's that first example there. Now I think it's important. I mean, I've got a process. For getting these problems done. I mean, the process starts with, for me, it starts with, understanding the ideas, and then very quickly having some formulas memorized. But then it's like, okay, when I see these, find the amplitude, period, phase shift, I'm just going to use my formulas to produce those values. And then the process of graphing starts. And I've got my process, and you guys are going to watch me do the process, I think, 4 more times. You don't necessarily have to follow my process, but I think you have to have a process. Okay? And so make sure that you've got your process kind of nailed down in the process of doing all those problems on your web assignment homework. Okay? Don't just continue to fumble your way through those problems. You want to kind of have it nailed down to where you're just working nonstop from start to finish and getting the job done. Okay, let's continue. As long as you guys don't have any questions, we can continue doing some more of these exact same kinds of problems. How am I doing on time? Oh, we're doing great. We're doing great, I think. we're doing okay. We're doing okay. All right, let's dig into the next one. All right, so now we got everything going on here. Number 5. Again, find the amplitude, period, and phase shift. Sketch the graph. So I guess if we're identifying parameters first, the A, here we're looking at A sine of bx plus c. My A is 7. My B is 1/2. And my C is pi over 4. If we want to find the amplitude is the absolute value of A, which in this case is 7. The period is 2 pi divided by the absolute value of B, which in this case is 2 pi divided by 1/2, which is 4 pi. And the phase shift is minus C over B, which is minus pi over 4 divided by 1/2, which is minus pi over 2, I think, when we work that out. So there's my amplitude, period, and phase shift. I guess if we wanted to circle our answers there. All right. I don't like that at all, but at least not like when, anyways, on your exams, you should kind of clearly identify your amplitude, period, and phase shift. And then we'll go ahead and use the book strategy of solving the inequality. 0 is less than or equal to 1/2 x plus pi over 4 is less than 2 pi. If I subtract pi over 4 from both sides, you get negative pi over 4 is less than 1/2 x is less than, that's 7 pi over 4 when I subtract pi over 4 from 8 pi over 4. And then remember with inequalities, you can always add or subtract anything from both sides with inequalities, and nothing weird happens. When you're multiplying or dividing on both sides, and you got to pay attention to whether or not you're multiplying or dividing by negative numbers. Here we want to multiply on both sides by 2, and we can do that. Since it's a positive number, we can multiply on both sides on all sides of this inequality by 2, and it doesn't change the direction of any of the inequalities. So a good interval on which to graph one cycle for this function is pi over 2 to 7 pi over 2. If we cut that in half, there's the midway point for our graph, 3 pi over 2. Like, one way you can do that, by the way, guys, is if you add the endpoints. If you add the endpoints and divide by 2, that gives you the average of the endpoints, which gives you the middle point. Anyways, the 1/4 of the way point is pi over 2, and the 3/4 of the way point is 5 pi over 2. Since we are dealing with a sine function, we're going to start at 0. Now, this is the cycle this is the interval on which we're going to graph a cycle, and the sine cycle starts at 0. At the next interesting point, it moves up to 1, but in this case, since our amplitude is 7, it's going to move up to 7. All right, so we start at 0, go up to 7, back down to 0, down to negative 7, and then back up to 0 for one cycle of this sine function. And if we wanted to continue on, let's see, it looks like we're getting our quarter of the way points, our quarter cycles every pi. As if you take your period and divide by 4, that gives you your quarter period. So if we go back a quarter period, we'll get back down to the -1. And then that's about as far as we can go here. There's nothing left to do out there. All right, so there's the graph. There's the graph here in number 5. Any questions so far about our process? What is the interval? What do you mean by that? Sorry, I missed that question. Oh, okay. Oh, sorry. I guess I forgot to answer. The interval here is minus pi over 2 to 7 pi over 2. Again, That's not a question that anybody's ever going to ask you to do explicitly. It's just one of the things that can be part of your process if you want to make it part of your process. I have a slightly different thing that I do. It's basically equivalent to this. So in the next problem, I'll show you like the work that I do instead of this. But again, all of this work, if you had produced none of this work, one, it's not part of the problem, or at least not anything that the problem asks you to do. Two, I wouldn't take any points away if you didn't do that on a quiz or a test. Three, even if you didn't have any kind of equivalent work shown, I wouldn't take any points away if you didn't have anything like that on the test. But I guess the key thing here is there is important work related to this that you will need to do. All right. I think there's a better way. I think a better way of getting the job done here. All right. So I'll go ahead and stop talking about it and just do it. Let's just go ahead and do it. All right, find the amplitude, period, and phase shift, and sketch the graph of the equation. I guess the the instructions are going to be the same every single time here, aren't they? All right, so our amplitude is going to be the absolute value of -4, which is 4. The amplitude is 4. The period is 2 pi divided by the b value, which is 2 in this case. So the period is going to be pi. And the phase shift is negative c, which is negative pi over 3, divided by b, which is 2. And so the phase shift is pi over 6. Pi over 6 when you work everything out. All right, so here's my strategy for getting the right interval. First off, I do my phase shift. Okay, I go out to pi over 6. And then I add my period. I guess I should... Oops, pi over 6. I should quarantine all my information here. So I start at my phase shift, and then I go out to my period, which is pi plus pi over 6. So right there. And then I do the process of cutting things in half. I guess I could label this as 7 pi over 6. The halfway point would be right there, which would be I'm going out of my mind. 2 pi over 3. And then the quarter mark would be right there, which is pi over 3. And then the 3/4 of the way mark is right there, is 5 pi over 6. All right, so I got, here's roughly where I have my phase shift and my period taken into account. And then we start to take into account the amplitude as well as any flipping that's going on. In this case, my amplitude is 4. Now, normally with a cosine graph, I would start at 1, but since the amplitude is 4, I would start at 4. But since we got a minus sign, I got to start at -4. Okay? So I start at -4, and then the rest of them kind of almost fill. Like once you have that starting one, the rest of them just kind of happen. Or at least for me they do. I guess maybe that's because I've been doing this for a while, but this business of just bouncing back and forth, -0, +0, -0, +0, -0, +0, whatever your amplitude is. And here, since we started negative, it's like -0, +0, negative. All right, we're done. And then we can sketch that one cycle in for our cosine graph. If we wanted to get more cycles in, looks like we're getting these tick marks at all of the pi over 3 numbers. So we'd have another one there. I guess let's just go ahead and put all those pi over 3 tick marks in. Or you could see here, well, then maybe that's not a good example. Sorry. All right, so 0, positive, back down to 0, negative, back to 0, positive. So there's another cycle and a half maybe. Now, when I give these questions, when I write exams and things like that, I usually tell my students specifically, give me 2 cycles, or give me at least 2 cycles, or give me at least 1 cycle or something. I don't think any of your homework problems are gonna. Well, here's the thing. All right, so I guess now's a good time to talk about this. Your WebAssign problems, you don't have to draw anything in WebAssign. You just have to pick the right graph. All right. So I think one thing that means is that you might get fewer attempts at some of those problems, because you might not, I don't know. But you might get fewer attempts at the multiple choice problems. The other thing is you're not going to be asked to pick out a graph on your test. You're going to be asked to sketch a graph. And so you should practice sketching graphs. You should not practice picking out graphs. You should practice sketching graphs. So when you're doing your WebAssign problems, practice sketching graphs. If anybody wants me to send them another file with a copy of some graph paper, if you want, I can send you a PDF that has this kind of graph paper. If anybody wants it, just send me a message and ask for it. I'm probably going to do that anyways. It might take me a couple days to get around to it. But practice drawing good graphs. Okay, I think we got 2 more of these, where I might show you some slight variations on how to find that interval, and get the period and phase shift part of your graph done. Same instructions here. Let's just go ahead and dig in. The amplitude here is going to be 5. The period would be 2 pi divided by pi over 4, which is 8. Yep. And the phase shift is negative pi over 2 divided by pi over 4. Which, oh God, that'd be pi over 2 times 4 over pi, which is 2. So our phase shift is 2. All right, now the marks that they've given us here, can I actually erase those, I wonder? No, I can't. That's disappointing. The marks that they've given are not going to be useful. Okay? I think it might be useful if we replace them with 2s, if we go by 2 instead. So that's going to be 2. That'll be 4. That'll be 6 and 8 and 10 and 12 and 14 and 16. And going backwards, -2, -4, -6, and -8. All right. So here's a variant. Here's a variation on how to find a good interval. We've got the textbook's inequality to solve, which is fine. And the last problem, I did my phase shift and then my period. Here I'm going to do my phase shift. I'm going to start with my phase shift again. There's my first part. And then I'm going to look at a quarter period. In this case, a quarter period, 8 over 4, is 2. And then my next tick mark will be at 2 plus 2, which is 4. And then my next tick mark will be 4 plus 2, which is 6. And then 6 plus 2, which is 8. And then 8 plus 2, which is 10. and now I've got my tick marks. Okay, so rather than get my interval and then cut it in half and then cut the halves in half, I can just cut it all in fourths right from the get-go and start and do that. Okay, so I'm going to graph this on the interval 2 to 10. Now notice if I had started with my phase shift and added my period, that would have given me 2 to 10. Or I guess just for the sake of it, if you had started with the 0 is less than or equal to pi over 4x minus pi over 2 is less than 2 pi, then if I add 2 pi everywhere, you get pi over 2 is less than or equal to pi over 4x, which is less than or equal to 9 pi over 2, right? 2 pi is 8 pi, sorry, that's 4 pi over 2. 4 pi over 2 plus pi over 2 is 5 pi over 2. Sorry about that. And then if I divide everywhere by pi, then all the pi's go away, and then multiply on everywhere by 4, then that's where you would get your 2. 2 is less than or equal to x is less than or equal to 10. That's where you would get that. Now, I think we just figured out why Dan doesn't do this, right? Did we all figure out why Dan doesn't do that? It takes too much time, and there's an easier way to get that information. That's why Dan doesn't do that. But that doesn't mean that you shouldn't do that. If that's how it works for you, then that's how you should do it. Anyways, either way you do it, we've got our important tick marks on the x-axis sorted out. Now we can go and think about the fact that, all right, since we are talking about a cosine function, we would normally start at 1. And since the coefficient here is a 5, instead of starting at 1, we're going to start at 5. All right, so we go positive, 0, negative, 0, positive. And then the rest is the same curve that we've been drawing for the last hour and 20 minutes, at least. If we wanted more periods, I'm going to be fine. I'm going to go ahead and stop here just so that you guys can also feel comfortable. The problem doesn't... I guess we'll go ahead and say, if the problem doesn't tell you otherwise, if you give me one good cycle, then I'll give you full credit. Fair enough? If you give me one good cycle, then I'll give you full credit on the graphing problems. Actually, I'm just going to go ahead. Can I open this without showing you guys the test? Yes, I can. No, I can't. That's not good. That's not good at all. I'm going to give you guys a different version of the test than the one you just saw, by the way. So the thing that you just saw is not relevant. Anyways, the problem on the test, God darn it. All right, so this was version C. I opened the wrong version anyways. Let's see, what does the calculator version say for this one? Here it says, all right, the instructions on your test are going to say find 5 key points and graph 1 period of the curve. That's exactly what I just did here, right? That's exactly what I just did here. 5 key points, and I graphed 1 period of the curve. Okay? So that's what you guys should be prepared to do next week on the test. By the way, please don't share that video with anybody. God. See, now I'm going to have to delete. All right. All right. Where'd my chat go? Okay, let's do one more of these, and then we can take a break. I think this is the last one I have of these. Yeah. And then we can take a break. Find the amplitude, period, and phase shift, and sketch the graph of the equation. The amplitude here is going to be the absolute value of -3 which is 3. The period is going to be 2 pi divided by that 4 right there, which is pi over 2. And then the phase shift is negative pi divided by 4. That's it. All right, C divided by B was finally nice. All right, the phase shift is pi over 4. Now here I'm gonna go ahead and relabel all these points too, just so that we have a good chunk of. No, actually no, I'm not. Let's get some practice drawing some graphs on some intervals that aren't. Well, the problem, Sean, is that this is going to be a video on YouTube, and anybody can go back and watch and pause whenever they want. Yeah. There's 2 versions of the test, though, and you guys are not going to get that version I just showed. And if I find out that someone outside of my class got a hold of that test because somebody in my class showed them the video, then we'll root somebody out and get them kicked out of school. So let's not cheat, guys. All right, so we have the amplitude, period, and phase shift. I'm going to go ahead and say, all right, I'm going to start at negative pi over 4, and then my quarter period is pi over 8. See, this is where things get obnoxious. So if I go back to negative pi over 4, then the second tick mark is pi over 8 later, and then pi over 8 later, and then there's positive pi over 4. Sorry, so positive pi over 4. All right, so there's my 5 key points. Since we're talking about a sine function, with the sine function, we always start at 0. And then we usually go up to -1 next, but since my leading coefficient since the a term here is -3, instead of going up to -1, we're going to go to -3. So another way of thinking of that. Well, I guess, Neil, the point here is that y'all are going to get a a piece of graph paper on your test that looks exactly like this. And so you kind of want to practice. If they happen to give you a wonky problem where you have to draw an ugly picture, you want to practice graphing ugly pictures. We're not going to have the opportunity to change the scale. I was going to change the scale, but then I decided not to, just so that we could see how to deal with it if we're not allowed to change the scale, like you guys will have to do on the test. Anyways, we start at 0 and then go down to -3 as our next step. So you can think about the a coefficient as either being where you start. The a tells you where to start, at least along the y-axis, for cosine, and tells you where to go first for the sine function. So we start at 0, go negative, back to 0, then go positive, and then back to 0. And then when I try to draw this skinny graph here the best I can, that's not too terribly bad. Now we'll go ahead and zoom in. I don't know that I can change the scale, but I can zoom in here so that we can see. We got pi over 4. This is supposed to be minus pi over 4. This is minus pi over 8. And that's positive pi over 8. And I would probably make your line go just a little bit through the dot just to indicate that this keeps going, but I'm not going to draw the rest of it. So again, the instructions on our test are going to say plot 5 points, and there's our 5 points. Plot 5 points, graph 1 cycle, and those are the 5 points and cycle that they intend. Now, if you get me 5 points and a cycle, I'll give you credit, but those are the 5 points in cycle that they intend and the ones that I want you guys to give me. All right. Like I said, you guys have lots and lots of graphing problems, not only on your web assigned homework, but there's also I think there's also 2 graphing problems on your take home quiz for next week. So if you didn't see the email from yesterday afternoon, what I want you guys to do is just go to the modules here on Ivy Learn. All of the quizzes for the entire semester are already here, and so take home quiz 3, you can download the PDF and print it off, or if you don't have access to a printer, just do the problems listed here. And notice here's our minus 2 pi to 4 pi picture that goes from minus 8 to 8, and oh my god, minus 2 pi to 4 pi picture that goes from minus 8 to 8 on the y-axis. So you got a couple of graphing problems to do that are just like the ones that I just got done doing on your quiz. Anyway, so sorry. If you aren't able to print this out, then try to stick to the format here. Like do whatever number 18 on page 427 is. Do that on the front page of whatever you turn in, and do number 427 on number 40 on page 427 on the back of that first page. And then on the front of the second page, do these 2 problems. And on the back of the second page, do these 2 problems. Again, just make sure that your quiz is formatted the same as everybody else's. It makes it easier to grade when everybody's work looks approximately the same. So we'll go ahead and take a break now. And we'll come back in 5 minutes and talk about section 6.7. All right, I think that's been about 5 minutes, so we can probably go back to getting some work done here. Those graphing problems took me a little bit longer than I thought they were going to. Just a little bit, though. Because I get distracted by trying to look at that test and then freaking out over the fact that I'm a little bit upset with myself about that. All right, I got to get over it, though. The next section is section 6.7, called Applied Problems. And so the bulk of the problems here are going to be story problems. That's what applied problems is a euphemism for story problems. The first batch of problems we're going to be, I guess one of the applications for trig is we can start to solve triangles. So I don't know if you remember in your geometry class solving triangles. That's one thing that we can do with trig. Now, in our textbook, there's a kind of a standard way that right triangles are labeled, and this is going to extend later on to a standard way that triangles are labeled. First off, you can label the corners of the triangle with capital A, B, and C. For right triangles, they're always going to put the C at the right angle. The corner where C is at the right angle. So A, B, and C are corners. And then we can also label sides. The side opposite capital A we're going to call lowercase a. And the side opposite capital B we're going to call lowercase b. And the side opposite capital C we're going to call lowercase c. So here's where the distinction between capital and lowercase letters is so essential. Okay? It's so essential. Capital letters are labeling corners and lowercase letters are labeling sides opposite. We can also label the angles. We label the angles. The angle in corner A, we're going to use the Greek letter alpha for that. Kind of looks like a sideways ribbon. I didn't even draw it very good there. The Greek letter alpha. The Greek letter beta. It looks like a B, but it's kind of got this little tail on it. And unlike the capital B, where I guess the top is a little bit bigger than the bottom, for the beta, the top is bigger than the bottom. Sorry, for the capital B, the top is smaller than the bottom. For the beta, lowercase beta, the bottom is usually the smaller of the two humps. And then the third letter of the Greek alphabet is gamma. We haven't talked about gamma yet. We talked about alpha and beta on the first night. We haven't talked about gamma yet. That's this lowercase gamma here is the third letter of the Greek alphabet, and that's the one that we're going to use to label the right triangle, the right angle when we're talking about a right triangle. Okay? So that is the standard labeling for our right triangles here, and that's how we're going to make sense of the next few problems. Given the indicated parts of the triangle ABC with gamma equal to 90 degrees, find the exact values of the remaining parts. All right, so we're going to start with our right triangle. Now, it doesn't necessarily matter. I guess the only angle that really matters is gamma. The other two don't really matter, alpha and beta. But then the sides have to be, all right, I guess for a right triangle, C is always going to be the hypotenuse. A is the side opposite angle alpha, and B is the side opposite angle beta. In this case, they told us that alpha was 60 degrees and that C was 6. And we're meant to use that information to find the remaining parts, figure out what, I guess, all the side lengths are, A, B, and C. Well, we know that C is 6. As well as what all the angle measures are. Well, I guess we already know that alpha is 60 and gamma is 90 degrees. We can quickly determine that beta, remembering that all the angles have to add up to 180, we can quickly identify that beta is 30 degrees. And then all that remains is figuring out what alpha and beta are. Now, if any of you out there are tempted to try to eventually use the Pythagorean theorem, well, first off, we need at least two sides, so we can't do that yet. And second off, it turns out that it's not even that useful. even when we know two sides. All right. Now, if I can think of, for instance, some trig relationships that relate side A to side C, there are a couple that we could use here. One of those would be sine of alpha is A divided by C, right? That's opposite over hypotenuse. Got my angle alpha here is A over C, opposite over hypotenuse. And we know two of those pieces. Sine of alpha, sine of 60 degrees, is the unknown A divided by 6. And so we can say, oh, we can solve for A here. A is 6 sine of 60 degrees. And if you're down with your unit circle, you know that sine of 60 degrees is root 3 over 2. And so side length A ends up being 3 root 3 once we simplify, once we cancel the 2's there, 3 root 3. Now, like I said, if we wanted to, we could figure out what side B is by using the Pythagorean theorem, but side B is not all that bad. Let's see, cosine of 60 degrees would be B over 6, right? Let's see, I got cosine is the adjacent over the hypotenuse. And so it's not a far or distant journey to see that B is 6 times cosine 60 degrees. And if you know your unit circle, cosine of 60 degrees is 1/2. Now, all these values, well, your calculator would have given you this value. Your calculator would have given you that value. But it maybe wouldn't have given you the exact value here. The problem wants the exact values of the remaining parts. So you kind of have to know your unit circle to be able to do this problem. Looking at part 2, we have a couple of sides that we know. Let's just go ahead and say this side is 4 root 3, which I guess would make that angle alpha. This side's always, or that angle's always gamma, so this side's always C, which is 8. We don't know side length B, so we can go ahead and determine that. So B, here's where we will use the Pythagorean theorem to say that B is the square root of 8 squared minus 4 root 3 squared, which is the square root of 64, minus 16 times 3 is 48. And the difference between 64 and 48, I think, is 16. So square root of 16, which is 4. All right, so now we have all 3 sides. We can also determine the angles. So, for instance, cosine of alpha would be the adjacent side 4 divided by the opposite side 8, which is 1/2. Now, there are lots of rotations or real numbers whose cosine is 1/2, but there's only one acute angle. There's only one value in the first quadrant where cosine is 1/2. If you know your unit circle, then cosine is equal to 1/2 for alpha equal to 60 degrees. Actually, we just did that, right? We just did that. I didn't intentionally pick this one to to work out to be the exact same triangle, or at least a similar triangle. It's not the same triangle, it's a similar triangle to the previous problem. And that must mean that beta is 30 degrees, because in a right triangle, the two acute angles have to add up to 90. All right, now we kind of rushed through the Pythagorean theorem. I think you guys have a reasonably good handle on using the Pythagorean theorem. But if you want to, if you need to take a few more seconds to work that part out, take some time to do that, maybe after the lecture tonight. But we just use the Pythagorean theorem to figure out what B was here. All right, we can do a similar problem. Given the individual parts, approximate the remaining parts. So let's go ahead and draw our triangle. I'll draw one that looks like this time, pointing to the left. All right, we have beta, angle beta. One of the angles is given to us. It doesn't really matter which one we call beta. The picture doesn't have to be to scale. There's angle alpha then. Side length A would be over here now, 20.1. And we don't know side length B or side length C. Now alpha, remember alpha and beta have to be complementary angles. So alpha is going to be 90 degrees minus 64 degrees, 20 minutes. That's supposed to be minutes there, not seconds. 20 minutes. And that should be what? 25 degrees, 40 minutes? If I want to make a full degree, I need 40 more minutes. And if I want, then I'm at 65 degrees, and I need another 25 degrees to get to 90. All right, so alpha is going to be 25 degrees, 40 minutes. Then I can use trig to find out the side lengths. Let's see. We have this angle here and this side length. If I want to find angle B, I need to use tangent. So tangent of 64 degrees, 20 minutes is equal to opposite B over adjacent 20.1. So that gives us that B is 20.1 tangent of 64 degrees, 20 minutes. Now here's where I'm going to go ahead and just use my calculator and say, let's see, 20 degrees. Let's get this screen a little bit further over here. All right, so 20 minutes is the same as 20 divided by 60 seconds. Sorry, 20 divided by 60 degrees. And if I add that to 64, there's my angle in exact degree measure. And then if I want to do 20.1 times tangent of that, am I in degree mode? I should be in degree mode. There we go. Enter. There we go. 21 times tangent of that answer. I get 41. 41. It says approximate. What do you guys suppose we should approximate to? I guess this was given to me with one decimal place, or three significant figures, if you like significant figures. So I'll just give my answer to three significant figures, so 41.8. 41.8. I can keep this on top. I don't want to keep it on top because I want it to go away. All right. So I had gotten a couple of messages before class today of some people getting some incorrect answers on WebAssign because they were approximating too soon. And so here's one way that you can use your calculator. This should be approximate down here, by the way. I'll do that. I'll fix that in just a second. Using the previous answer button on your calculator or the store button on your calculator, I think you should be able to store a few different values. Is there an A, B, a C on this? See, my calculator has like an A, B, and C. Doesn't look like this one does. But you should be able to store values as well to use them later. Anyways, we wait until the very end here to approximate this. So the B side is approximately 41.8. And then, again, I could use the Pythagorean theorem to figure out what C is, but let's just go ahead and do some trig instead. If I do the trig function that relates my known side and my known angle to the unknown side length C would be cosine of 64 degrees 20 minutes is adjacent 20.1 divided by hypotenuse. And so there's where we can solve for C and get C is 20.1 divided by cosine of 64 degrees 20 minutes. All right. So I'll get the calculator out again, and I'll just get this all done at once. 20.1 divided by cosine of 64 plus 20 divided by 60. I hate the fact that this calculator uses a division sign so much. Anyways, it gives me approximately 46 point what now? 46.4. Okay. That seems a bit small to me. That seems a bit small. And so maybe we can use the Pythagorean theorem to check. All right. Let's do that. All right. If I do 20.1 squared plus 41.8 squared, and then take the square root of that, yay, I got to check my answer. So that's one of the nice things about you have a couple different ways of doing the problem, then you can do the problem one way and then use the other way to check your answer. So that's a nice way to maybe avoid making some of the sillier mistakes. So solving triangles is not all that bad when you have numerical values. Here's one. Given the indicated parts of the triangle ABC with a right angle gamma, we want to it says express the third part in terms of the first two. Hi, son. I just saw your response and it took me a second. There is a little bit of latency involved in the live stream, and so you guys see something like 10 seconds after I actually do it. Anyways, let's think about, we have angle beta here and side length B as well as side length C. Now the relationship between these three components here, this angle and these two side lengths, is sine of beta is equal to B over C. And now it wants us to express B in terms of the other two. So solve for B. In this case, that's pretty straightforward. Just multiply on both sides by C, and I got B is equal to C sine beta. Okay, that wasn't too bad. Let's see if the next one is any scarier. If I draw, I got angle B down here, side length B over here, side length A over here, and side length C over here. Let's see, I don't even want to worry about B. I'm trying to express C in terms of beta and A. Well, the trigonometric function that relates that angle to those two side lengths is cosine. Cosine of beta is A over C. And we actually just did this problem. If I want to solve for C now, I can multiply on both sides by C and get C cosine of beta is equal to A. and then divide on both sides by cosine of beta. I get C is A over cosine of beta. Or if you wanted to call that A secant of beta, that's fine too. Now we don't have a secant button on a calculator, and so we wouldn't be able to do any calculator work with this version. But that's a cleaner looking version. There's no fractions. So one of the ways that trig functions are nice is that you kind of never have to worry about fractions. We have reciprocal identities that allow us to not really ever have to worry about fractions if we don't want to. So that's nice. All right, so I guess that's the long and short of solving for right triangles. My experience the last time I taught trig is that the students, they didn't necessarily like solving for right triangles, but they liked those problems because they did very well on them. They eventually found them to be not very challenging. It's another opportunity for us to practice understanding our right triangle trig relationships, in addition to doing some of the computational work that we've been learning about the last couple of weeks. Looking at, and so by the way, all the applications that we're concerned with, there are other applications in this section. The ones that we're concerned with are all right triangle applications. Okay, so I guess I almost skipped over that on your, where is that? There it is. That's not it either. On your notes, do I have, the applied problems. Okay, so the primary strategy for working through story problems in this section. Again, these are just the story problems that we're concerned with. There are other story problems that we're not concerned with. The problems that we're concerned with, the key thing here is that we're going to be using right triangle trig to get the answers. So you want to read the story, draw a good picture. Sometimes a picture's given to you. I don't give you any pictures here. The test doesn't have any pictures. So you want to be able to maybe read the story well enough to produce a good picture. In your picture, you should be able to find a right triangle. And if you're able to label that right triangle with the values that you know, along with the ones that you don't know, and in particular the one that you're trying to find, if you can identify the side or angle of that right triangle that you're trying to find, then you can set up a trig equation just like the ones that we've been doing, and solve the triangles, and then answer the question posed by the story. Now that those steps there are going to get us a good 95% of the way. But in most stories, there's going to be some part of it where you're going to have to just stop and think for a moment. All right. So there, you guys are going to see some problem types on your homework that maybe I didn't do a problem like that tonight. That's where you're going to have to stop and think and maybe figure some things out. You guys have been doing a pretty good job of figuring things out. I've been leaving that to you guys. It's an important part of the course. Is I can't tell you all the things. There's just not enough time, and so. You guys have been doing a good job of looking at problems and sorting some things out on your own, and that's one of the things that you're meant to do in this course. It's a growth thing for this course. So keep doing that when you get to the story problems on your homework. Keep doing that. If you end up having some trouble with one, as always, don't hesitate to ask a question, and I'll help as much as I can. So let's dig into some of these. We have first a surveying question. It says, from a point 15 meters above level ground, a surveyor measures the angle of depression of an object on the ground at 68 degrees. Approximate the distance from the object to the point on the ground directly beneath the surveyor. Okay, so the idea here is we have level ground. And then I guess there's a cliff. There's a cliff with a surveyor. I can draw a better man than that. Oh, God. Oh, God. We got a surveyor up here. That's better. All right. And he is looking at an object on the ground down here. Okay? Point 15 meters above level ground. So I guess that means that this height right here is 15. It says the angle of depression of an object on the ground. So we're looking at an object on the ground, and the angle of depression is this angle right here. Basically, if you think of like an observer right at this level, like how far down would they have to tilt their view to be looking right at that object? Okay, so that is 68 degrees. Approximate the distance from the object to the point on the ground directly beneath the observer. So that is this distance here. We can call that maybe distance D. All right, now there's our picture. We need to find the right triangle. Well, there's a couple of places where there's a right triangle, but I'll go ahead and just draw the right triangle in red here. There's a right triangle. Now we have two side lengths of that triangle. Actually, we have one side length, and we're trying to find the other. We don't know anything about the hypotenuse. By the way, there's the right angle. That's the part about this being level ground. Level ground. If I go straight down from the observer, then the ground doesn't add any more angle to that. It's a right angle. Go straight down from the observer, then go straight out to the object. It's a right angle. Now, you may have remembered some things from geometry. There's a pair of parallel lines here. We've got this line here and this line here. These are parallel lines. And we've got this line that's coming through and bisecting those lines. And there's this theorem in geometry that says that opposite angles, like these two angles right here, are the same angle, as well as these two. This one right here and this one right here. So that's one way to identify that this is 68 degrees. Another way that you could have identified a relevant angle is this is a right angle right here as well. And so this angle is complementary to 68 degrees. So that angle, God, this is a messy picture all of a sudden. That angle is 22 degrees. All right, now our picture's really messy. We have the key thing is that we've identified our triangle. And so once you've got your picture and your triangle, it's not always a bad idea to pull that triangle off to the side with some of the key components. Okay? There's 68, there's 15, there's this side that we want. There's a trig function that relates those two sides. That one angle and these two sides is tangent. Tangent of 68 degrees is opposite 15 over adjacent D. And we're trying to determine what D is. So D, when I solve for D is 15 divided by tangent of 68 degrees. And when I bust out the calculator, 15, still in degree mode, 15 divided by tangent of 68 gives me about 6. They don't tell us how to round here, so I might be round to 3 decimal place. I know that's my default. I don't know why it's my default. It's my default. So about 6 point over the 3 decimals, 060. And our units are feet, meters. What are they? Meters. All right, so I think the most troubling thing here was dealing with this angle of depression. Another thing, we might run into it in another problem, angle of elevation. I guess the idea is the way that I think about it is, imagine if you gaze straight out horizontally, the angle of elevation and the angle of depression are basically, how do I have to adjust my gaze in order to see the thing that I want to see or go the place where I want to go. Next one, here's another. All right, angle of elevation is another thing that's going to happen here. Airplane takeoff. We have an airplane takes off at a 10-degree angle. I guess the point, it's a 10 degree from horizontal. 10-degree angle from horizontal and travels at a rate of 250 feet per second. Approximately how long does it take the airplane to reach an altitude of 150 degrees? 15,000 feet. I can't even read. Reach an altitude of 15,000 feet. All right, so we've got, I guess, our sea level and our airplane. I'm not even going to try to draw an airplane. Our airplane takes off, and it makes an angle of 10 degrees. At some point in time, the plane's in the air. It's got an altitude of 15,000 feet. There's our right triangle. And they want to know, how long does it take? How long does it take? So they want a time. So this is one where we had to put on our thinking cap. Okay? In terms of the distance, they ask us how far did the plane travel? That would be the hypotenuse. I'll just call it C. All right, if it asks us how far did the plane travel before it hit 15,000 feet, that would be the hypotenuse C. Or I guess you could say, how far did the plane travel through the air? Okay? And we have trig. We can use trig to relate the angle that we were given, the 10 degrees, with those two side lengths. Here it's opposite over hypotenuse. That sine of 10 degrees is 15,000 over C. So C should be 15,000 divided by sine of 10 degrees. All right, let's use the calculator here. 15,000 divided by sine of 10. Now I'm going to go ahead and keep the calculator answer, so I'm not worried about saying that. Right, this is about 86,381 feet. 86,381 feet. All right, now the problem here didn't ask us how far the plane had traveled through the air. It asked us how long it took, what time. And this is where we have to incorporate the velocity or the speed that they gave us. 250 feet per second. And so, all right, if I guess one way to solve that, well, I'm just going to treat this like a conversion problem. I can convert my 86,381 feet into seconds by multiplying by the, I guess I'm thinking about this fraction as 250 feet per 1 second. And if I flip that fraction, 1 second per 250 feet, that allows me to cancel the feet. So there's a few different ways of dealing with this conversion. For me, this is the easiest way. You can set up a proportion. You can say 250 feet, 250 feet per 1 second should be in proportion to 86,381 feet in some unknown number of seconds, and solve for X. That's another way to deal with that problem. Or you can use this is definitely one that's usable, the TI-30XS. They don't let you use it at IUPUI, but you can definitely use that here, and I would recommend using that one here. Or, see, there's a lot of different ways. I guess off-road teaching, the question here is, how do I use that velocity to get the job done? And different students have different experiences with those things. Another way to deal with this is to know that velocity is distance divided by time. And so if you wanted the time, you could rearrange that equation and do distance divided by the velocity. So there's a few different ways to deal with, going from an answer in a distance answer to a time answer. And we're just kind of exploring those different ways. Because that's one of the complications that comes up. Anyways, when I take my previous answer that I still have now and divide by 250 feet, now I'll go ahead and approximate my answer to the nearest whole number. All right, 346 seconds. So t is about 346 seconds, which I don't like. We'll just talk about minutes. That's the same as how many minutes? 5 minutes. 5 minutes and 46 seconds. So a little bit less than 6 minutes. Okay. So here we have an angle of elevation of 10 degrees. That would be how that would show up in this problem. Looking at the next problem, this is a geometry problem. So this one's kind of challenging. It says a regular octagon is inscribed in a circle of radius 12 centimeters. So first off, what that means is, I'm going to try to get a halfway decent circle here and a halfway decent octagon. If I start with a circle, that's not half bad. Inscribed means on the inside. So we have an octagon on the inside of this circle. Here's where I'm trying to get a good octagon going. This is not going to be the most amazing thing ever, but it's not going to be all that terrible either. That one's definitely disgusting. All right, so there's our octagon inscribed in a circle. You can also have circumscribed. Circumscribed would mean, the octagon is on the outside of the circle. Okay, so they want us to approximate the perimeter of the octagon. This bottom side here this side is awful. I did okay everywhere else, but that side is just pathetic. And I guess this side too. See if I can fix that just a little bit. Just a little bit. Oh man, I really messed that up now. How did I screw that up so badly? My circle wasn't perfect. Okay, there we go. Now we have an octagon. So the idea here is that I've got 8 sides. If I label them with S, the perimeter will be 8S. Now here's a setup that if I didn't show you guys the setup, then some of you might have figured it out on your own. Some of you may not have, but I think the expectation is that not many would have figured it out. Okay, and so they intend for me to show you how to do this one. All right. The idea is if I start at the middle, they gave us the radius of the circle, right? That's the radius of the circle, 12. Now, if I draw one of these radii to every single corner, then I'm able to make a bunch of triangles. That's something that you can do with every regular polygon. Regular here means that all the side lengths are the same. You can do with every regular polygon. And so, well, it's not a right triangle. There's a triangle here. There's a triangle where I know 2 of the sides, and I'm trying to find the third side. Okay, 2 of the sides are the radius, 12. And the other side is the side I'm trying to find. Like I said, it's not a right triangle. And so we're not able to use anything that we know yet. Before we make it a right triangle, though, I'll give you a second. Here's where I would ask a question in class and give you guys a second to think about it. Can anybody think about how to find the measure of that angle. Given that, well, there's one of those there, and one 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 there. There's 1, 2, 3, 4, 5, 6, 7, 8 of those angles, and they come together to form a complete rotation. So someone out there is screaming, whatever this angle theta is, I can find it by taking my full rotation, 360 degrees, divided by 8. Or maybe everyone out there is screaming, Dan, shut up. It's 360 divided by 8. And I've already done it on my calculator. And you're wasting my time right now. 360 divided by 8 is 45. All right, so that angle is 45. Now, we're not actually going to end up using 45 degrees. What ends up happening is when we want to make a right triangle out of this, I drop an altitude, if you remember that terminology from geometry, drop an altitude to make a right angle. All right, so now let's draw the right angle. My triangles are all crooked all of a sudden. All right, I know one side of this triangle is 12. The other side now is 1/2 of S. Okay, that altitude cuts this side in half. Because this is an isosceles triangle, I've got two sides that are the same length. Because I have an isosceles triangle, the altitude bisects the angle theta. So, hey, that tells us that this angle right here is 45 degrees divided by 2, which is 22.5 degrees, I think. So it tells us that, all right, the angle not only gets bisected, but the opposite side gets bisected as well. All right? And now I've got a known angle, a known side, and then another side, and I can relate everything with some trig. We have that sine of 22.5 degrees is equal to 1/2 S over 12. That's the same as S over 24. And so the side length that I'm looking for is 24 times sine of 22.5 degrees. And then before I do anything on my calculator, I could find that side length. Remember, ultimately, I'm trying to find the perimeter. The perimeter is going to be 8 times that side length. So 8 times 24 times sine of 22.5 degrees. And I can get all my computations done at once. So sometimes it's beneficial to just, instead of using the previous answer button on your calculator, just write down what you need to compute and then just do it all at once. 8 times 24 times sine of 22.5. And since my original my radius was given to me with 3 significant figures, I'm just going to go ahead and give my answer to 3 significant figures. And so that would be 73.5. What were our units here? 73.5. I think our units were centimeters, maybe? Centimeters, yeah. Is the video stuttering? I'm not seeing anything. I'm not seeing anything on my end. All right, there might have just been a hiccup on Sean's end. Anyways, 73.5 centimeters here is the perimeter of our octagon. Now, we could do all sorts of fun things with regular polygons, and back in the day they used to, we could do all sorts of fun things with polygons. I'll just leave it at that. You can do all sorts of fun things with polygons and cutting things up into triangles, but we'll maybe save that for another time. Circumscribed, by the way, is spelled with an I, not a U. Circumscribed. Stopped and is spinning around. Maybe a little page. All right, on to number 7 here. Ladder calculations. A ladder 20 feet long leans against the side of a building, and the angle between the ladder and the building is 22 degrees. So we can draw this situation right off the bat. We got a building. There's our building and our ladder. And the angle between the building and the ladder is 22 degrees. So there's a halfway decent picture. Approximate the distance from the bottom of the ladder to the building. So I guess there's ground here, and this is the distance from the ladder to the building, and there's our right triangle. Now the ladder is 20 feet long, so the hypotenuse of this triangle is going to be 20, so that's known. And it wants us to approximate the distance from the bottom of the ladder to the building. All right, so let's see. We can say that sine of 22 degrees is the side opposite of that angle, which is d, divided by the hypotenuse, which is 20. And so the distance is 20 sine of 22 degrees. Awesome. Awesome sauce, Sean. I can't believe I just said awesome sauce. Um, 20 sine 22 degrees. There's nothing left to do there. All right, let's do the calculator work here. 20 sine of 22 degrees. So that would be about, I'm going to go ahead and go 3 decimals here. I know it's arbitrary. I never remember to think about the numbers. 7.492. .492 feet. All right. So that one was pretty straightforward once we got our picture drawn. B, if the distance from the bottom of the ladder to the building is increased by 3 feet, approximately how far does the top of the ladder move down the building? All right, so this is where there might be other more clever, efficient ways of getting the job done, but we'll call this D1 now, and this side height 1. We're going to need to find that first height, the original height here. Height 1 is going to be 20 times cosine of 22 degrees, right? So if what do these say these arrows do? Oh, these are the ones. Oh, these. I have no idea what those arrows are doing. Anyways, 20 cosine of 22 gives me about 18.544. 18.544. Okay, so then once our ladder shifts, we have a similar picture, but it's slipped further away. Now the bottom of the ladder is a distance d2 away from the wall, and the ladder goes a height h2 up the wall. The ladder is still 20 feet long. And says approximately how far does the top of the ladder move down the building? Well, first off, D2 is just 3 plus D1. It's 3 feet away, 3 feet further away. The distance increased by 3 away. And then we're saying approximately how far does the top of the ladder move down the building? So they don't actually want height 2. We have, I guess, the previous scenario, there's a height 1. We want this distance right here. They want the difference between those two heights. So they want height 1 minus height 2. All right, height 1 we already have. That's 20 cosine of 22 degrees. Height 2, we don't know any angles now. I guess here our only option is to use the Pythagorean theorem. We got 3 side lengths. Okay, so this is a little bit messy, guys, but that's okay. 3.0 plus that first distance. Well, let's all right. D2 squared plus H2 squared is equal to 20 squared, right? And so then height 2 is the thing that we're trying to find. Height 2 would be the square root. Why did I say 20 degrees? It's 20 squared. Height 2 would be the square root of 20 squared minus that D2, this D2 length squared. Okay? The D2 length squared, 20 squared, minus 3 plus the first length. And then that first length was 20 sine 22. So 20 squared minus 3 plus 20 sine of 22 degrees squared. All right, so that's my second height. Now, I've been working without, I think it's reasonable to be using your decimal approximations the whole way here. All right? But I would encourage you to, see what you can get done without using your calculator. All right? Push yourself hard to see what you can get done. You'll start to get a lot better at this, and you'll be a lot faster. And so now we just have to do one thing on the calculator. 20 cosine of 22 minus the square root of 20 squared minus parentheses 3 plus 20 sine 22 in parentheses squared in parentheses. Enter. All right. So the thing slid about 1.5 feet down the wall. Okay, so I made that one, the work here, a little bit more obnoxious than it absolutely needed to be. But I guess the point here is that there's a lot of intermediate values. And if you start doing decimal approximations at every single intermediate value, one, you're picking up your calculator a lot and spending a lot of time punching buttons on the calculator and a lot of time writing down these numbers. Okay? Whereas if you can train yourself to just work algebraically, symbolically, without doing calculator work, once you pick up a little bit of speed there, it actually isn't all that bad. And then you only have to pick up your calculator at the very end of the problem. Now, to be fair, this one was nastier than most are. This one was nastier than most are. And so, but they're just something to try. I didn't figure this out myself until like a second semester physics class. And then once I kind of figured out this trick of, just write algebra until you get to the very end and then pick up the calculator, I realized how much faster it was. Do we have time for... Well, we don't have time for these last two. I'll go ahead and do a video probably tomorrow afternoon. I'll work through these last two problems. There was also some question, and you guys had some trouble with some of the solve the trig equation problems from the 6.3 homework, I think it was. So I might throw some of those problems that you guys have been struggling with on homework. I might do some examples of those as well. So be on the lookout for an after party video to pop up sometime, maybe tomorrow or on Friday. Like I said, I'll probably get around to doing it tomorrow. But anyways, that's all I want to do tonight. Again, sorry for having to get this done on YouTube. But I think doing it this way is going to be a lot better than, like I said, the coordinator, before I was able to tell him what we were doing, the coordinator got a hold of me and he's like, Dan, so we're going to go ahead and push your test back a week, and then we're going to give you 2 whole weeks to get through 3 weeks worth of material for the second test. And oh, by the way, 3 of those 6 sections are like the hardest sections of the entire semester. And I was just like, dude, that doesn't work. So we're going to do this on YouTube instead. And he's like, yes, that's a much better idea. So hopefully this worked out as well as it could. And if you guys have questions, please let me know. I'm getting sick. I'm hearing myself say that, but it's always true. Please ask for help when you need it. As long as you guys don't have any other questions in the chat, I'm going to go ahead and end the stream here in about 30 seconds. All right, you guys have a good night too. I appreciate you coming by and watching. All right, have a good night, everybody.